interpretations of run-2 analyses and implications for BSM physics. So it's myself, Darren Price, and Michael, who will be joining us later in the week, who will be convening the session. So the aim of my slides now is not to give you an overview of current interpretations of all run-2 analyses for BSM physics, because we would be here until at least the end of the day. So despite attempts when I was writing these slides to go down the rabbit hole in that direction, so I held myself back. So what I've tried to do is just give a very brief overview of a few, just 1 or 2 examples of some classifications of particular types of reinterpretations that have been done. Ooh. Okay. Reinterpretations that have been done, and a few points to consider on them, some of which link into the other working groups. So the first one, and the one that's perhaps the largest use case and where the most activity sits inside the collaborations, but which I'll discuss the least, is the dedicated RICO-level BSM searches. So, of course, there are a huge range of these dedicated new phenomena searches inside Atlas, HCB, CMS. Along with the kind of core limits they set on specific models in these measurements, one key thing for reinterpretation is that these measurements come along with an extensive, exhaustive list of supporting material to enable reinterpretation at the RICO level. So this includes things like reinterpretation of these signal limits in some parameter space in terms of a variety of other sort of benchmark models, but also additional auxiliary material that allows for comparison with other models in the future. The issue, or the key limitation of these dedicated RICO-level searches, of course, is that they're inherently model-dependent, some more than others, but all of them to some extent are model-dependent. You can mitigate this model dependency, which really comes in maximally when you look at a specific model and set limits on a particular parameter space in a particular model. Very hard to interpret that in anything that doesn't very closely resemble that very specific model. But to mitigate that model dependence, in addition, what's usually provided are signal grids for a variety of other models with different types of topologies. Also, as an example, you see here efficiency and acceptances integrated over particular kinematic variables for the measured objects for a variety of different models, because the PT dependence, the multiplicity of the objects and so on play a role in the efficiency that you observe in the detector. Of course, these aspects of what you provide alongside the sort of core result will be discussed in a different working group, but perhaps this is somewhere where there's a clear link for discussion between the 2 working groups here. Of course, there are always limitations on reuse of these kind of searches when you move to any unanticipated topologies. If you take some SUSY search as an example of here, and then go into a region where you've got boosted jets and you haven't done an analysis with boosted jets, for example, or if you try to extrapolate outside the original phase space of the measurement, you can run into problems, in particular because of requirement of accurate detector simulation to fold the theory model with, which may have limited validation in these new regions that haven't been explored before. And also, how do you fully validate the efficiencies and acceptances when the object kinematics and made the object, not just the object kinematics matter, but also the multiplicity, the presence of other objects, and so on. How do you know that your simplified detector simulation is doing a good job in that very strange topology you might pick for your new physics models, such as some of the ones we heard yesterday, or one very topical one at the moment is long-lived particle searches. And there's a question, even if you provide all of the necessary tools to do this, how do you fully capture the model dependence? You could do a variety of different models, but to some extent you're always open to the possibility of running into problems of validity in some area of phase space. So these are some of the challenges which face the RICO level searches. I'm now going to move on to standard model measurements as the sort of core part of this talk, because that's somewhere where it's perhaps less obvious in the past. I mean, I think that people in this room know this, but in the past, less obvious that you can use these widely to reinterpret in terms of BSM models. There have been a variety of theory papers which have performed studies of this. So this is one example taking now old, but Atlas WW cross-section measurement and interpreting an excess that was present at that time in terms of BSM models. So you can see here from this paper, this is one example. The black points are the differential cross-section data measured by Atlas. This is corrected for detector effects, efficiency, and acceptance. And then at that time, there was a slight excess above the standard model backgrounds. You can see shown by the sort of light cream color. And you could fill in some of these excesses with this red data here, which was this particular compressed SUSY model. So this was one way that you could show that where some BSM models actually fit the data better at that time, and alternatively, you can use this to also constrain the model space of these BSM hypotheses. A critical thing to mention here, which comes up a lot in discussions of reuse of the standard model cross-section measurements, is that these measurements are perhaps it's a misnomer to call them standard model measurements, because they explicitly do not assume a standard model hypothesis in the measurements. You are measuring standard model particles, but really you're measuring, if the measurement is set up correctly, you're measuring final states, rates of production of final states, and any model dependence, any residual model dependence in those efficiencies and acceptances are habitually taken into account and included in the systematics. And you can actually estimate this model dependence from an in situ validation against your data. So you can tell how much in the extrapolation from the RICO level measurements to the particle level cross sections, how much extrapolation you're doing and how much variation away from the standard model is actually consistent with your data in the first place. I'll talk a little bit more about that later. Another place which has been a very active place for reinterpretation of standard model measurements is in effective field theory fits. These electroweak measurements in particular are very good interpretation candidates for this, looking for new phenomena in high energy tails. And differential cross sections, of course, are particularly sensitive because you bin this differentially. So one interesting feature here is that although measuring things like diboson production shown here, we usually provide unfolded cross sections and the correlation information to go along with that. So far, it's been very typical to characterize any new phenomena using an EFT at the RICO level. So you see an example here of the transverse mass of the WZ system, data points and theory, and then you could, of course, look in a high energy tail to look for new phenomena. Typically, what's been done in the past is to have some cutoff in your RICO level quantity and measure the rate of measured production, compare it with the standard model rate, and then set limits on your new phenomena at RICO level. But of course, you could do this using the particle level data as well, as long as the correlations are provided. One thing that might be interesting to characterize and really assess properly is the gain and loss that you get from doing a RICO level fit of the FT parameters versus a particle level fit. It's often been discussed that RICO level fits are more accurate, more precise at excluding certain parameter space, but largely that's been because the RICO level measurement's been driven with the FT parameterizations in mind, whereas the unfolded particle level cross sections have not. However, if you designed particle level cross sections directly with setting BSM limits in mind, you might achieve similar or better performance. That's something I'll touch upon later as well. So you might ask the question more generally, can these AGGC limits be reinterpreted in terms of constraints on specific new particles in extensions of the standard model, or is this just some generic deviations that you're trying to capture here? In particular, you might have some concerns that for a specific model, you might choose an inappropriate energy scale cutoff. When you derive your ATGC limits, you always have an energy scale cutoff in your limits, or you can push this to infinity and get weaker limits. And depending on where you put that energy scale, might characterize what type of new physics phenomena you're really sensitive to. If you put your cutoff here and you have some new particle at some higher energy scale, you're okay. If the particle is showing up at a lower energy scale, though, you might get inappropriate limits, either over or underestimating. And another issue with current ATGC approaches, which are done at the RICO level by inside the experiments, is that you're typically not scanning over all the parameters in the Lagrangian simultaneously. You usually just fix one and then scan across another. But however, there have been papers that have shown that this can work. Here's one example from a year ago, which showed that you could take particle level data on diboson production and use it to constrain BSM coefficients in particular theory at various energy cutoffs. And yeah, just one example here. There's some discussion in this paper, which is potentially interesting for this working group, that discusses how presentation of the full likelihoods is important for combinations, and I think that'll come up in another working group. But also that talks about the benefit of driving these limits on unfolded data if you have the correlation information, because you can do multi-dimensional fits to multiple differential distributions. Here's another example from earlier this year of measuring electroweak WJJ productions. You're looking at this kind of process here, and sensitive to anomalous triple gauge couplings in this vertex. In this paper, there was, again, the standard procedure of setting ATGC limits on some parameters at the RICO level, but in this paper as well, Atlas also provided unfolded differential cross-sections of various observables. One here is the leading jet PT, that you can actually compare against standard model prediction and various CP observing and CP violating ATGC parameter variations from the standard model. One thing that might be useful to look at now that this data is on HEP data is, can you achieve these same ATGC limits after the fact from the unfolded data distributions once you have the correlation information provided as well? And if these limits were set purely on the leading jet PT, if you include additional differential distributions that are studied in this paper into that global fit, can you actually improve your sensitivity overall as well? Here's one example of how these global fits can be extended then beyond a single measurement. So before I was talking about multidimensional differential distributions in a single observable, in a single final state process. There have been examples, though, of combining diboson data from Atlas and CMS and using that to derive constraints on Higgs coupling parameters or vice versa. So you can see how there's having unfolded measurements allows you to do easy comparisons between Atlas and CMS, and this is discussed in this paper here. And you can see that you actually get complementary constraints from both these data sets. You have the Atlas WZ and WW measurements here, which combined with Higgs constrain these ATGC parameters much more than any one individually. There's also a few other studies, I just pick out a few here, of where diboson data now at RICO level have been used to constrain Higgs couplings. So this is where looking at a global picture to try and find BSM deviations can be very important. So you can actually constrain the Higgs sector using triple gauge vertex data. You see here a range of operators. Red shows the constraints you get from purely from Higgs data. Blue is when you include the triple gauge vertex data as well. So for some operators, you see that the sensitivity improves dramatically. Vice versa, the Higgs measurements now have also been used to constrain new phenomena using EFT approach on unfolded differential cross-sections. So in this paper here by Atlas published differential cross-section measurements as a function of 5 different observables. Here is shown the ratio of those observables to the standard model, shown in, can't see, oh, sorry, this is the double ratio of data to theory divided by data to some BSM hypothesis. So you see how different BSM hypothesis either changes the rate overall or changes the shape in some of these distributions. If you add this information on theory data and the covariance matrices, which are also provided alongside this, then what you can actually do is set limits on the Wilson coefficients. You see some examples here. Standard model is this black point and black point, and then the 1 and 2 sigma contours constrained by this data. So you see that it's got a lot of constraining power. And this is something you can reproduce after the fact as well. As well as EFTs, very generic models, Higgs differential cross-section measurements, shown here, just a function of the diphoton PT, have also been used and been reinterpreted in terms of specific BSM models. So one example here was the standard model cross-section for Higgs production undershot the differential cross-section data at particle level at the time. And this, in 2 example papers here, was used in one case to fill this in with some dark matter model that better fit the data, and in another case was used to constrain couplings to the charm and the B sector. So you could actually test the Yukawa couplings of the Higgs after the fact from published differential cross-section and correlation information. Going beyond looking for high energy tails and deviations in the FT models, you can also see the power of these sort of standard model measurements for things you might not expect, such as bump hunting. So this paper here actually went and tried to perform a Dijkjet resonance search using unfolded data. So just do your standard double differential cross-section measurements as a function of the Dijkjet mass in various rapidity bins, shown here. Compare this to the theoretical predictions, and then you can actually do a bump hunt, a scan across this mass distribution to try and set limits on quark compositeness and so on. Of course, this analysis exists at the RICO level, but then has some of the problems of reinterpretation that I mentioned earlier. So one thing you might want to attempt is do a Dijkjet bump hunt on this, where the systematics to the model dependence are already built into the systematics assigned on these data bins. The interesting result from this is that the scale on the compositeness scale in a particular model was actually very close to the dedicated RICO level search at the time. So you weren't really losing much in sensitivity from doing this bump hunt after the fact on unfolded data compared to a dedicated search for Dijkjet resonances at the time. So this was a very good demonstration of the reusability of standard model measurements for something that you might not expect. One thing we could discuss is the possible limitations of this approach. Of course, when you get to an edge case, when you get to a bin where you don't have any standard model data after background subtraction, you lose your ability to have sensitivity, of course, of those masses. That might not be a problem at the RICO level because you still see some data, even though if it's all background, you can still perform a hypothesis test against it. So right in the tails, when you get down to statistical issues of low statistics, you may run into a problem of reach. But certainly in the bulk of the distribution, you can reproduce these measurements after the fact very, very straightforwardly. This brings me to another aspect, which is another paper here looking at standard model production of tri-boson final states. How you can use unseen standard model processes to actually set limits on new physics as well. And this might go some way to a direction to take these kind of unfolded cross-section measurements in the future in these high energy tails. So this kind of measurement is sensitive to anomalous quartic gauge couplings, this kind of vertex here. This paper actually had no observation of that process, but turned this around and set 95% confidence limits on the cross-sections, shown here, and then provided the correlation information as if in the same fashion as you would if you were providing a differential cross-section measurement. So as long as this information is provided, you can actually still use this data. You can still use this data to constrain BSM theories, and this is an example here setting some limits on some contact interaction. And there's a lot of discussion of the benefits of this possible approach in this paper here. And this is a possible way forward when you get into the really low stats tails of a distribution. If you want to unfold these distributions, usually you have to cut off in your high energy tail where you have limited statistics because you have instabilities in the unfolding and so on. But you could turn this around and in those bins potentially provide cross-section limits and still correlate all the systematics from the bins you do observe the process into the bins you don't, to keep the sensitivity that you might have to high-scale physics in those regions. And then one thing to finish with that's relatively new, from just a couple of months ago, that takes this idea a little bit further, is I've talked about unseen standard model processes and making unfolded cross-section measurements of unseen standard model processes now to set limits on BSM. But what if we take this approach a step further and look for unseen BSM processes and unfold those as well? So it sounds a bit mad, but the new approach here is essentially to take this idea from the standard model cross-section measurements previously, but construct an observable which you correct for detector and efficiency effects that's sensitive to some generic new phenomena, in this case, missing energy plus one or more jets. So the observable here is rather simple. You essentially measure the rate of missing energy plus jets over the rate of dilepton, opposite sign dilepton plus jets in a very similar phase space to benefit from theoretical and systematic cancellations. And then you measure this differentially as a function of various degrees of freedom of that system. And then later, after the fact, after you've corrected those measurements for detector effects, you provide those measurements at unfolded to particle level, along with the statistical and systematic correlations within and between any distributions you unfold, the theoretical correlations on the standard model and the BSM, a rivet routine to encode all this information, and also the standard model numerator and denominator, so that critically you don't have to even have a standard model prediction. You can just plug in your BSM prediction into this model and see what it gives you. But we also allow the facility to replace this should, for example, a better standard model prediction come available in the future. Different aspect to reinterpretation, not just reinterpreting in terms of BSM, but reinterpreting if you get a more accurate SM prediction in the future. These are just some examples of the correlation matrices here. So this is what's measured in this paper. The missing ET in a MET plus one jet phase space, missing ET in a MET plus two jet style VBF style phase space, the dijet invariant mass, and the azimuthal angle between the two jets. And basically in the standard model, this should be flat up to slight differences in the phase space in the numerator and the denominator. So you see some slight deviation from that. But basically, this is a measurement of the Z invisible width in a sort of standard model hypothesis shown in red. But then now this is unfolded to particle level. You can actually add in any BSM model you like into the numerator and see how that modifies the standard model template. And then perform a likelihood test against the BSM hypothesis and the standard model hypothesis against the data to set limits on a variety of new physics models. So you see here, for example, there's a simplified monojet dark matter model which has a high missing ET tail. But then when you go into a VBF style phase space, for example, down here, you have very little sensitivity to monojet signals, but you do have sensitivity to VBF Higgs divisible models shown here. So what does this do for you? Well, critical thing about this is that this data can be easily reinterpreted in terms of various models. It's straightforward combined with further data in the future. Something to discuss perhaps is the limitations of this approach, reuse cases, and if there are possible other kinds of measurements you could do that are sort of very inclusive and generic like this in future. Flash some examples from this paper of where this was then reinterpreted using exactly the same inputs that you could take right now in terms of a monojet simplified model where the limits actually beat the dedicated monojet search using the same data set. A generic VBF EFT model where limits beat those from indirect searches, which is shown in grey, and a Higgs to invisible model where the limits were equivalent to those from the dedicated search using the same data set. So it really shows the power of this approach for reinterpretation. So I'll finish here with some thoughts. So we, of course, have direct dedicated BSM searches at RICO level. These are extremely extensive. Issue here, big issue, is assessing model independence or dependence. Potential difficulties in detector simulation. You have to generate standard model backgrounds, validate them, and assess the uncertainties appropriately. So this is a large overhead to reinterpret at RICO level, and these are really the challenges on that side. Standard model process measurements, however, have been widely used already for reinterpretation, both specific models, EFTs, in combination of electroweak sector data with Higgs data for specific BSM theories, for unfolded measurements where there's no standard model signal present, and for resonance searches. Again, model dependence is important here, but is accounted for, or should be, perhaps it's a point for discussion, in systematics on modeling in the theory. But of course, a critical thing again here is to ensure that the relevant data is provided alongside those measurements to allow for reinterpretation, and that's done in a consistent way, which I think is something that will be discussed in the other working group. You can extend the standard model concept to generalized searches for new phenomena. Test example case I just showed a few slides ago. be interesting to know potential use cases of such data for reinterpretation beyond the three BSM theories I just showed, and discussion on other generalized and folded searches in the future that might be valuable. For this point and for this point, there's questions of statistical issues you run into in the high-energy tails, where there's no standard model expected, or where there's no BSM expected. You have slightly different statistical questions about how you reinterpret, and limitations and model independence of such approaches as well. Looking forward then, what we would like to do is get towards a global picture for LHC BSM limits in the future. How can we combine all BSM search and measurements results in a single picture down the line? And how can we make best use of the standard model measurements? Are there any measurements we're actually missing to sort of patch together to make this complete picture of the LHC? And there are various ways of characterizing this. There's various approaches exist we can discuss, and also maybe there are other approaches. One thing to end with as well, which I didn't touch upon, but might be worth thinking about for this working group, is potential future use of CMS and Atlas open data. Both Atlas and CMS have released various data sets, and in CMS's case, this has already been used for some standard model measurements. But if we want to make use of this for reinterpretation in terms of BSM in the future, what do we need? What are the use cases? And is there any potential interest that we can take back to the collaborations to spur developments in this area? Okay, thank you. So are you talking about in the unfolded measurements? So that's done at the background subtraction stage. So normally you'd place yourself anyway in a... No. So at the point at which you do the background subtraction, you would assess